Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn the Mealy to Moore conversion. And we will see that if we have a state diagram of the Mealy machine, then how to convert it into the state diagram of the Moore machine. So we already know that in the state diagram of the Mealy machine, both inputs and outputs are represented on the arrow itself. While in case of the Moore machine, if you see, then the input is represented on the arrow while the output is represented on the state itself. So by following the certain conversion rules, it is possible to convert the state diagram of the Mealy machine to the Moore machine. So for this Mealy to Moore conversion, first we need to check all the incoming transitions to the state. So in this case if you see, then there are total 2 incoming transitions to the A state. So in the one transition, the input is 0, while in the second transition, the input is equal to 1. But if you see, then in both the transitions, the output is equal to 1. So in this case, we have a same output for the two transitions. And since we have a same output for both the cases, so we can write the output in the state itself. That means for all the incoming transitions to the state, when their outputs are same, then we can write that output in the state itself. So this is the equivalent Moore representation of the given state. But suppose we have a different outputs for the different incoming transitions, then we need to split that particular state. So in this case if you see, then for the two incoming transitions, we have the two different outputs. So here we cannot represent the two outputs within the same state, because in the Moore representation, the each state will have the specific output. That means here we need to split this A state into the two different states. So in this case, it has been splitted into the A1 and the A0 states. So as you can see, in the A1 state, the output of the machine is equal to 1, while in the A0 state, the output of the machine is equal to 0. So here, for that incoming transition for which this output is equal to 1, that transition will go to the A1 state. And likewise, the second transition will go to the A0 state, because in the second transition, this output is equal to 0. So here, for all the incoming transitions, since we have only two different outputs, so the original state is split into the two different states. But suppose we have a three different outputs, then we need to split the original state into the three states. So for example, in this case if you see, then here for the three incoming transitions, we have the three different outputs. That means here for the 0 0 input, the output is equal to 0 1. Likewise, for the 0 1 input, the output is 0 0, and similarly for the 1 1 input, the output is 1 0. So here we need to split the original state into the three different states. So let's say that is equal to A1, A2 and the A3. So as you can see, in the A1 state, the output of the machine is equal to 1 0. Similarly, in the A2 and the A3 states, the outputs are 0 0 and the 0 1. So now for that transition for which the output is equal to 1 0, that transition will go to the A1 state, because in this A1 state, the output of the machine is equal to 1 0. Likewise, for that transition for which the output is equal to 0 0, that transition will go to the A2 state. So here, when the input is 0 1, then at that time, we will have a transition into the A2 state. And likewise, when the input is 0 0, then that transition will go to the A3 state. So in this way, for all the incoming transitions, depending on the number of different outputs, we need to split the original state. So now so far we have seen that what to do with the incoming transitions to the specific state. But similarly, let us also talk about the outgoing transitions from the specific state. So let's say in the A state, there are total 2 incoming transitions, and also we have total 2 outgoing transitions. So the one transition is from A to B state, and the another transition is within the A state itself. So let's say this transition is 0 1, while the transition from the A to B is equal to 1 1. So here for the two incoming transitions, since the outputs are different, so this A state is once again splitted into the two different states. Now when the state is splitted into the n number of states, then its outgoing transitions will also get copied into the newly generated states. So here, the outgoing transitions of this A state will also get copied into the A0 and the A1 state. So as you can see over here, in the A state, when the input is 0, then it will remain in the same state. So here, in the equivalent Moore representation, we will also have the same transitions for this A0 and the A1 state when the input is equal to 0. Because here both the states are created from this A state itself. So in this A1 state, since the output of the machine is 1, so for this transition, it will remain in the same state. Because in this transition, as you can see, the output is equal to 1. That means in the A1 state, when the input is 0, then it will remain in the same state. But for the same input, if you see the A0 state, then it will do a transition from A0 to A1 state. Because in this A0 state, if you see, then the output of the machine is equal to 0. And therefore, for this specific transition, it will go to the A1 state. So similarly, in the state diagram of the Mealy machine, if you see, then whenever the input is 1, then we will have a transition from A to B state. And at that time, the output is also equal to 1. So in this case, if you see, then since we have only one transition in the B state, so we can say that in the equivalent Moore model, the output of the machine is equal to 1 in the B state. And now, from both A0 and the A1 state, when the input is equal to 1, then they will do a transition into the B state. That means for the Mealy to Moore conversion, for the each state in the state diagram, we need to check the incoming as well as the outgoing transitions. So for the incoming transitions, if the outputs are different, then we need to split that specific state. And after the splitting, the outgoing transitions for the newly generated states will be same as the original state. So to clearly understand the conversion procedure, let us take couple of examples. So this is the state diagram of the Mealy sequence detector, which detects the 1001 overlapping sequence. And in fact, in the earlier video, we have already drawn this state diagram. So let us convert it into the state diagram of the Moore machine. So first, let us look at the incoming transitions for the each state and let us see in how many states we require the splitting. So if you see this A state, then in this A state, we have the two incoming transitions. And as you can see, in both the transitions, the output is equal to 0. That means here, there is no need of splitting this A state. Similarly, let us see this B state. So in this B state, we have total 3 incoming transitions. And out of which, for the 2 transitions, the output is equal to 0, while for the 1 transition, the output is equal to 1. That means here, since we have 2 different outputs, so we need to split this B state into the 2 states. So let's say that is equal to B0 and the B1. So let's say in the B0 state, the output of the machine is equal to 0, while in the B1 state, the output of the machine is equal to 1. So similarly, now let us see the C state. So in the C state, we have only one incoming transition. And that's why there is no need to split this C state. So similarly, now let us see this D state. So if you see this D state, then once again, there is only one incoming transition. And that is why there is no need of splitting this D state. So in this way, we will have total 5 different states. Now out of these 5 states, in this A, C and the D states, if you see all the incoming transitions, then for all the transitions, their output is equal to 0. For example, in this A0 state if you see, then for both the incoming transitions, the output is equal to 0. Similarly, in the C and the D states also, the output is equal to 0. Therefore, in the equivalent Moore representation, in these 3 states, the output of the machine will remain 0. And similarly, in this B0 state also, the output of the machine will remain 0. That means only in this B1 state, the output of the machine will become 1. So now, to find the equivalent Moore representation, first let us start with this A state. And first of all, let us see all the incoming transitions. So as you can see in this A state, when the input is equal to 0, then it will remain in the same state. That means in the equivalent Moore representation also, it will remain in the same state. Similarly, from the D state, when the input is 0, then there is an incoming transition to the A state. So in the state diagram of the Moore machine, this is how we can represent it. So in this way, we have covered all the incoming transitions in the A state. So now, there is only one outgoing transition from the A state, that is from A to B state. That means whenever the input is 1, then there is a transition from the A to B state. And during this transition, the output is equal to 0. And here, since the output is 0, so in the equivalent Moore representation, it will go to the B0 state, because in this B0 state, the output of the machine is equal to 0. So similarly, now let us see all the incoming transitions in the B state. So in the B state, we have total 3 incoming transitions, and out of which, for the 2 transitions, the output is equal to 0. So in these 2 transitions, where the output is 0, those 2 transitions will go to the B0 state. So here, this is the one transition from the A state. And similarly, in the C state, when the input is 1, then it will go to the B0 state. Now in the third incoming transition, if you see, then the output is equal to 1. And therefore, this transition will go to the B1 state. That means here, from the D state, when the input is equal to 1, then it will go to the B1 state. So in this way, we have also seen all the incoming transitions of this B state. So now, let us see the outgoing transitions from this B state. So in the B state, we have total 2 outgoing transitions. The one is from the B to C state, and the second one is within the B state itself. So in the equivalent Moore diagram, this B0 and the B1 state will also have the same outgoing transitions. Because like I said earlier, this B0 and the B1 states are created from this B state itself. So here in the B state, when the input is 1, then it will remain in the same state. And at that time, the output is equal to 0. So in the Moore diagram, in this B0 state, when the input is equal to 1, then it will remain in the same state. Because here, in the B0 state, the output of the machine is equal to 0. That means for this input, it will remain in the same state. But for the B1 state, that is not the case. Because in the B1 state, the output of the machine is equal to 1. That means in the B1 state, when the input is equal to 1, then it will come to the B0 state. So now, the next outgoing transition for this B state is from B to C state. That means whenever the input is 0, then it will do a transition from B to C state. So here, in the equivalent Moore diagram also, this B0 and the B1 state will also have the same transition. That means here, in both B1 and B0 states, when the input is equal to 0, then they will do a transition into the C state. So in this way, we have covered all the outgoing transitions in the B state. So now, similarly if we see the C state, then we have total 2 outgoing transitions and the 1 incoming transition. So out of which, we have already covered the 1 incoming transition and the 1 outgoing transition. So now, the only remaining outgoing transition is from C to D state. That means in the C state, when the input is 0, then it will go to the D state. So in the equivalent Moore diagram, this is how we can represent it. That means in the C state, when the input is 0, then it will go to the D state. And similarly, in the D state, we have 2 outgoing transitions and the 1 incoming transition. And as you can see over here, we have already covered all these transitions. So this is the equivalent Moore diagram after the conversion. So like I said, the diagram which was given to us was the diagram of the Mealy sequence detector. And this is the equivalent state diagram of the Moore sequence detector. So if you have watched the previous video, then in that video, we have already seen the design procedure for designing this Moore sequence detector. And during the design, we got this state diagram. So if you compare this state diagram with the state diagram which we got after the conversion, then both are identical. So here, instead of the E state, we have a B1 state, and instead of the B state, we have a B0 state. Otherwise, both the state diagrams are identical. That means if you know the Mealy to Moore conversion, then you can easily convert the Mealy machine to the Moore machine. So let us take one more example so that the procedure will get clear to you. So here, we have been given the state diagram of one Mealy machine. So now, let us find the equivalent Moore diagram. So first, by looking at the incoming transitions, let us find out whether we need to split the states or not. So here in the A state, the three transitions are looping back to the A state, while there is a one incoming transition from B to A state. That means here we have total 4 incoming transitions. So out of the 4 transitions, if you see, then for the 3 transitions, the output is equal to 1, while for the 1 transition, the output of the machine is equal to 0. So in short, for all the incoming transitions, we have total 2 different outputs. That means here, we need to split this A state into the 2 different states. Let's say that is equal to A0 and the A1. So in the A0 state, the output of the machine is equal to 0, while in the A1 state, the output of the machine is equal to 1. So similarly, now let us see all the incoming transitions to this B state. So if you see this B state, then we have a one incoming transition from A to B state. And apart from that, the 3 transitions are looping back to the same state. That means in this B state, we have total 4 incoming transitions, and out of which for the 2 transitions, the output of the machine is 0, while for the 2 transitions, the output is equal to 1. So once again, since we have 2 different outputs, so we need to split this B state into the 2 different states. Let's say that is equal to B0 and the B1. So let's say in this B0 state, the output of the machine is equal to 0, while in the B1 state, the output of the machine is equal to 1. That means here, during the Mealy to Moore conversion, we will have total 4 different states. That is A0, B0 and the A1 and B1. So in the A0 and the B0 state, the output of the machine will be 0, while in the A1 and B1 state, the output of the machine will be equal to 1. So now, to find the equivalent Moore representation, first let us see the transitions of this A state. So here as you can see, the 3 transitions are looping back to the A state. That means whenever the input is 0, 0, 0, 1 and the 1, 0, then the machine will remain in the same state. So since these 3 transitions are looping back to the same state, so in a way we can say that they are also the outgoing transitions for this A state. And therefore, this A0 and the A1 state will also have these same transitions. So in this diagram of this Mealy machine, when the input is 0, 0, then the output is also 0. That means in the A0 state, when the input is 0, 0, then it will remain in the same state. Because in this A0 state, the output of the machine is equal to 0. While for the same input, if we see this A1 state, then it will do a transition from A1 to A0 state. Because in this A0 state only, the output of the machine is equal to 0. Therefore, for this 0, 0 input, we will have a transition from A1 to A0 state. So similarly, for the 0, 1 and the 1, 0 input, the output of the machine is equal to 1. So for these 2 inputs, from the A0 state, the machine will go to the A1 state. Because in these 2 transitions, the output of the machine remains 1. Similarly, for the same input, if you see the A1 state, then it will remain in the same state. Because in this A1 state, the output of the machine is equal to 1. That means for these 2 transitions, we will have a loop back into the A1 itself. So in this way, we have covered all the transitions which were looping back to the A state. So apart from that, we have another incoming transition from B to A state. That means whenever the input is 0, 0, then there will be a transition from B to A state. And at that time if you see, then the output of the machine is equal to 1. So for this B state, this transition is the outgoing transition. And here, since both B0 and the B1 are created from the B itself, so these 2 states will also have the same outgoing transition. That means from the both B0 and the B1 state, we will have the outgoing transition into the A state. But in this case, since the output of the machine is equal to 1, so from both B0 and the B1 state, we will have a transition into the A1 state. That means whenever the input is 0, 0, then from both B1 and B0 state, we will have an outgoing transition into the A1 state. So similarly, now let us see all the incoming transitions of this B state. So as you can see, the 3 transitions are looping back to the B state itself. And in a way, they are also the outgoing transitions for this B state. That means here, both B0 and the B1 state will also have the same transition. So out of the three transitions, when the input is 1, 0, at that time, the output is equal to 0. So from the B0 state, for this 1, 0 input, it will remain in the same state. But if we see the B1 state, then it will go to the B0 state. Because in this B0 state only, the output of the machine is equal to 0. Likewise, for this 0, 1 and the 1, 1 state, the output of the machine is equal to 1. So in the Moore diagram, for this 0, 1 and the 1, 1 input, if the machine is in the B1 state, then it will remain in the same state. Because in the B1 state, the output of the machine is equal to 1. But for the same input, if the machine is in the B0 state, then it will do a transition into the B1 state. So in this way, we have covered all the transitions which is looping back to the B state. But apart from that, there is one more incoming transition from A to B state when the input is equal to 1, 1. And at that time if you see, then the output is equal to 0. So since it is the outgoing transition for this A state, so both A0 and the A1 state will also have that same transition. That means in the equivalent Moore diagram, when the input is 1, 1, then both A0 and the A1 state will go to the B state. But in this case, since the output is 0, so for this 1, 1 input, we will have a transition into the B0 state. So in this way, we have covered all the transitions in the state diagram. And after the conversion, this is the equivalent state diagram of the Moore machine. So if required, then instead of this A0 A1 and B0 B1, we can represent these states as ABCD or with any other name. So in this way, we can perform the Mealy to Moore conversion. So similarly in the next video, we will see that how to convert the state diagram of the Moore machine into the Mealy machine. So if you have any questions or suggestions, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.